Relative rate of change, or a growth or decay rate, is when you have a percentage increase or decrease sort of as your rate of change per unit of time. And this is a little more complicated than obviously our absolute rate of change, and it's closely tied with our exponential functions. And we're going to look at sort of why and throughout this video, and also how can we find that sort of annual growth rate. Now, when we deal with that annual growth rate within a function, we're going to often sort of show it in its decimal form, but when we talk about it within context, we're going to want to turn it back into percents. All right, so I'm not actually going to talk about the formula first. I'm going to sort of come back to it as we work some problems, and I think it will make more sense. So we're going to start with sort of a population problem. So we have Canada's population in the year 2000. So we're going to just write year 2000. And that population was 30.69 million. And then in 2017, the population had risen to 36.71 million people. Now, if I'm thinking about this sort of in the context of this problem, we have 17 years that went by. All right. And if we're thinking about this as a relative rate of change, what that would mean is like, okay, it's the year 2001. And, if I multiplied this by some sort of percent, value, I would get a new population. And, in 2002, if I took that new population and I multiplied it by the same percent value, that would get me a new population. And I would keep multiplying by this value 17 times, and eventually I would get to this sort of final value down there. So it's sort of like, if I knew this annual growth rate, that would be the number that I'd be multiplying by 17 times, but I don't know it. That's the problem. But the key here is that it's a multiplication problem. And if you think back, well, what did I do back in the day when I sort of wanted to undo my multiplication? Well, I divided. But I'm not looking for the division problem that divides me directly from here to here. It's a little more complicated than that. But let's start there. What would I need to multiply 30.69 by to get to 36.71? Well, 36.71, that new value divided by the original value, would tell me, like, if I just wanted a single number to multiply by, that would be it. But the reality is that we want a number that we would have multiplied by 17 different times. So to sort of undo that multiplying the same thing 17 different times, we actually raise this to a fractional power. And I'm going to show you how to do that in the calculator in a minute. And so you'll sort of see this function or this expression right here and where it connects to sort of our equation up here. So notice we have the new value of the output divided by the original value of the output. And then if we raise it to the 1 over the time, sort of the time that's passed, this is going to help me find my annual growth rate, sort of. So let's go to our calculator really quick so we can take a look at how to put in that fractional power, because we want to make sure we can sort of figure that out. So if we go visit our Desmos calculator, I'm going to type in some parentheses here. And so we have 36.71 divided by 30.69 parentheses. So we're going to do this A to the B button right here. And this should exist also if you're using your phone version of this app. Now, when I put fractions in the power, I always get nervous they're not going to keep both numbers in the power. So I like to add extra parentheses. And so I put a little parenthesis here, and then I'm going to do 1 divided by 17. And I'll close out my parentheses, and ta-da! I have a number. And so it came up with 1.01 something, something, something. So we have this equals 1.01059. Now, this is not the annual growth rate. This is actually 1 plus the growth rate. Because when you're thinking about percentages, and we did this with taxes, when we did taxes in previous units, if an object is growing, we keep 100% of what's there, and add in the sort of annual growth, the annual sort of growth percent. So when it comes to sort of dealing with that in decimal form, that's where this -1 comes into play, because we're going to need to sort of take out that 100% because we only want to pay attention to the part that it grew. So I know I'm running out of space, but I'm going to write it sort of small. So we take that 1.01059, we're going to -1, and we'd get just 0.010, and we'll round that to 6. And I want to turn this into a percent, so I would multiply that by 100. I'll do little arrows over here. So that would be about 1.06% was the annual growth rate. So a little connection to how it's being built and then how that formula works. So now let's look at this in some context. And in these cases, we're actually already given that sort of relative rate of change, but how can we then use it and sort of building our way to that exponential function formula that we'll be focusing more in on our next video. Okay, so we have the price of milk, and it's been rising by 3.7% each year. And we're told that 2 years ago, the price was $2.77, and we want to know what is the price today. So we're going to sort of start like the last one and think about this in a table of values. So in year 0, that was 2 years ago today, it cost $2.77. 1 year goes by, and that milk is going to go up 3%. So if it's increasing 3%, remember that's 100% of the original price plus the 3.7% increase. So the reality is we need 103.7% of this $2.77. So we're not going to multiply by the decimal of 3.7%. We're actually going to multiply by 1.037. And that would get us our next price point, which was about 2.8725. And then that would be 1 year later. So then if I want 2 years later, I would multiply by that same growth rate again. Because remember, we're dealing with multiplying. It increases by 1% every time. And so this time it would be 2.979. And so we could say that the cost in 2 years would be $2.98. Now notice, we multiplied by the same value twice. And if we think a little bit about our exponent rules, multiplying by the same number twice is the same thing as taking that number and squaring it. And then we originally multiplied that 1.037 by the 2.77. And if I put just this expression in my calculator, guess what I'd come out with? And let's just test it out. So if I go to my calculator and I put in 2.77 and I times that by 1.037 and I raise that to the second power, 2.98. So I get the same thing I got by sort of working it out step by step in my table. And keep that sort of expression in mind. It's going to come up again. All right, let's look at a slightly different one. So this time, instead of growing, our function is actually falling. We're decreasing by 22%. So let's talk about what that means. That means instead of adding that 22% each year, we're going to take the original 100%, but we're going to be minusing 22%. And so that sort of factor that I'm going to be multiplying by every time is going to be the decimal equivalent of 78%, because each year we only have 78% of what we had the previous year. So we're looking at the price of something. So today, the price was $1,477.99. In 1 year, it's going to drop 78% of what it used to be. And that happens to be $1,152.83. And then in 2 years, it drops again the same amount, because remember, it's a constant relative rate of change. And that time now it's 899.21. So that would be the sort of cost of my TV. And again, just like the previous problem, if we sort of think about that in terms trying to condense it, we multiplied by the same 0.78 twice, and we had that initial value, and then our output was that $899.21. Why I'm stressing that so much is if we go down, and we're going to skip a little bit ahead just to sort of take a sneak peek, and you take a look at the exponential function formula. Notice we have that initial value. That would be like that 1,477.99. The 1 plus or minus the relative, and this piece right here, it builds right off that 100% minus the 22% to get that 78%, that number's in the middle. And then our exponent is the input letter, or in this case, the time that went by. So what we've done within a table with our relative rate is we've basically done an exponential function without formally doing an exponential function. And that way of thinking is totally acceptable. It's a great way to start with these types of problems. It's more important we sort of get how those percentages work than like have the perfect equation set up. So now in thinking still about these percent growths and decreases, we want to look at just turning something that's not given to us in an annual rate into an annual rate. It's good to be able to sort of keep in mind how much something grows over a year versus a month. So if prices increase at a rate of 4.5 monthly, we want the annual growth rate. So if you're thinking about increase, keeping in mind, that means every month, whatever the original price is, I would be doing 100% plus that 4.5% every month. So if I think about that in decimal form, that would be 1 plus 0.045, or it would be multiplied by 1.045 each month. Now, how many months are in a year? Well, there are 12 months in 1 year. So I'm going to be multiplying by that 1.045 12 times. And in the previous problem, we multiplied by that 0.78 twice because we had two sort of units of time going by. But here, since we have 12 units of time going by, I'm going to want to multiply this by this factor 12 times. Well, I don't actually want to multiply by it 12 times. That's what exponents are for. So if I just raise it to the 12th power, that's going to give me, what is this, instead of multiplying 12 separate times, what could I have multiplied by once to come out with the same value? And in this case, that would be 1.6959. Now, just like when we talked about with some of this earlier problem up here with the Canada population, that's not actually my annual rate. That's the 100% plus the annual rate. So remember, we have to take out the 100%. We want to think about it as like 1 plus R, and we want just the R. Well, in this case, if I subtract out 1, I'm going to end up with 69.59, and I want to say percent increase. And it's always good to reference that it's going up versus going down, whether you put it sort of like an increase afterwards or you put a positive number. But you want to differentiate, because if we look at this next problem, we're looking at a decreasing rate monthly. So it's going to be the same idea, except instead of adding, we're going to be subtracting that 0.045. And so we would actually get sort of every month, we would have a different we would have 0.955 would be the number we multiply by. So just like last time, I'm going to take that factor and I would be multiplying by that 12 times, sort of throughout the year. And so instead of multiplying it by 12 different times, I could just instead multiply by 0.5755. Now, this is not my annual growth factor, because remember, this is the result of taking 100% plus my rate. And I want to know, what is that rate? So if I subtract out 1 from that, I actually get negative 0.425. And you might be going, why is it negative? Well, it's negative because this is going to be a percent decrease. So this actually would be a 42.5% decrease. And notice they're not the same. And that's okay. They're not necessarily going to be the same when I'm looking at an increase versus a decrease. Sort of decreasing exponential functions will act slightly different than growing ones. And so this should give you a sense of sort of that rate portion of our exponential function. And we're going to dive deeper into that exponential function equation in the next video.